0 days. First of all, I'd like to say hello to all of you, and I'd like to thank the organizers for this opportunity. It's a pleasure to be here, and what I'm going to tell you will help us to become even crazier. There are two fantastic lectures, and of course this will be for you perhaps less problem or problematic or cumbersome than my paper. I see there's some late comers to my presentation. Today's presentation will deal with exploiting, and more than this, people talk about vulnerability in the case of 0 days. What about the steps to find vulnerability, and how can I go for it? Because there is like a void there. So it is true that my paper is of a higher level. I've tried to simplify this for all of you to follow my presentation, and then as you're going to get the paper published, you could study it and take your time. My name is Antonio Morales Maldonado. As you all know, I work as a security researcher at GiftHub, and I work with a team. It's GiftHub Security Lab team, and we find vulnerability in open source projects. We've disclosed vulnerability, and we help developers to correct vulnerabilities. We're also creating a group of companies pro-open source. We have universities, companies, associations, part of the coalition of open source, and our security lab.github.com. You can find all our projects. As a matter of fact, you can just go fall asleep. Some people yesterday had a fantastic evening. I come from the southern part of Spain. Who am I to tell you what you should do? Now let's motivate you, but not this one, because I know that there are people motivated here, and some people follow Aznar here. But I'm going to tell you that there is something real here. We have some vulnerabilities we found here, and I would like to go on to practical grounds, not only theory. Recently encountered vulnerabilities in well-known softwares, and I'm going to show you the methodology with whom I found vulnerabilities. I'm going to tell you that I understand there are people who are less technical and might not have the same information. I'd like to tell you where is hidden here. In the slides here you will see there are, in 2 or 3 slides, there will be hash. The hash will be at the bottom left part of the slide, and the person who's able to find the hash and knows the content of the hash, so will tell me the flat text corresponding. Raise your hand. I have here some merchandising from GiftHub. I have some t-shirts, some small devices for you, and there'll be a reward for those telling me the content of the hash. We're going to start with the first vulnerability I found. It was found in this well-known server, and it pro FTPD. The vulnerability was reported a month ago, and we have the memory pools of the pro FTPD. And memory pools are here, as you see, corrupted, and thanks to this active transfer, which could be interrupted. Vulnerability is exploitable, and this could derive onto other vulnerabilities. I know what you're asking. Memory pool, what's a memory pool? How on earth, what is it? What is it? Because I use Python for programming. Memory pool is use of pools. Those are resource collections to manage dynamic memories. The one you reserve with malloc, new, and memory pools have advantages. We could reduce fragmentation of your functions. Let's imagine in your program, the way you program things, we call malloc and new, and we're releasing this afterwards. This could be of a different size, so memory could be fragmented, and we will have a less performing device. Dynamic memory at the same time, if we invoke manually or we reserve memory, we have to release this afterwards. A memory pool has the advantage of releasing the memory pool. All the resources associated into the memory pool will be released immediately. So there is another thing here, which is why not to create memory pools. And that's something I got here. And you see how it describes the reality of many of the programmers nowadays. The person writing a code, there is another colleague or the boss telling, what are you doing? Well, I am now preparing a library, but that does exist. I didn't know about it. Well, the truth is that some other people libraries are not as good as mine. So I'm going to go for it again and redo it, whole thing. But reuse what already works. Reuse what is working, reduce what is good. And this server prof FTPD is an old server. Back in 2003 it was widely used, and that's why we use a memory pool. They use a memory pool, or they copy the memory pool from a software like Apache, and it is the same memory pool. What I'm going to explain will help you if you use Apache. And here we have the way it works from Pro FTPD on your right up here, the upper part of the slide you see lifetimes according to the duration required. On top of this you have a global pool, and down there you have a pool associated per request. When you have a request, a pool is created. When it is ended, it's deleted. So they are organized from the last duration on top till the short duration ones. For those knowing data structure, it's like a linked list of resources, and this resource list will have several fields: the content of the memory on the one hand, a link towards the next element on the list, and at the same time there is a link toward the last element of the list. That's a memory pool, simplified version of it. And we see the way we work with memory pool. Instead of calling the functions the malloc or the calloc and so on, we call, and we have here, we have pcalloc, tmalloc from proof FTPD. When we reserve memory blocks of big sizes that are added to the list, we go and we see if there is a free memory, and if it is not, then they call malloc and they add another memory part at the end of the list. We're adding memory at the end of the list, and at the same time, in order to optimize resources, we have a list. We have a list of free blocks, and in order to, if we have a P free, which is a free version of Pro FTPD, if we have free blocks there, they don't need to make a call to malloc. So it wouldn't then have another load of resources. We're not invoking malloc or free. We're just managing the blocks, reducing fragmentation. And after what I have said, and it's a bit boring, I know, we have the vulnerability. This is a pool, and vulnerability specifically is there because when you create a pool and we require to add a new block at the end of a list when there is no memory free, when there is no memory left as within the list of free elements, and we need a new one, if we're able to send the command while transferring information on the data channel FTPD, FTPD won't send us a free element. New block should send us information on a free block that to be added at the end of a list. But we could do it differently and to get an element included in the pool. And let's have an idea. If we get a block that's already been included as part of a list and we put it at the end of a list, what we're provoking is that we're closing the list. We're just having a last element linked to the first one that's corrupting the list. because the first element, the next and the first available will be corrupted. So we'll have basically a pool that will be totally corrupted, a total corrupted pool. P is a pointer pointing towards the pool, and green elements are the content of corrupted elements. We see that's not a valid memory value. So we'll have a lower length, and that means chaotic situation, total chaos, because whatever memory invoked dynamically won't be valid. Any invoke won't be valid. And on the top of this, that's not easy to detect. You'll know ASAN, ASAN, address sanitizer. Address sanitizer implements the interceptors. Interceptors of address sanitizer are hook, so to have hooking towards certain functions that could be compromised regarding security issues. We see the functions here of managing strings are hooked. And then if I implement address sanitizing, I'm invoking this function, and the one I'm calling is the address sanitizing function, controlling or checking that I have a proper management of memory, and if there is something wrong, if there is a bug, I'll be informed. But if we implement a memory pool, which is not a common thing in small projects, but you have it in Apache, in Chrome, Google Chrome also, they have their own memory pool. It's a big project. In those big projects, if we use address sanitizer, the functions of managing dynamic memory like pcalloc, malloc won't be hooked. With address sanitizer, we won't be able to find the bugs. So this is why the simple approach won't allow us to find bugs in the projects. What we find here, it's that we see in the side damaged things, we can just get part of the vulnerability. In my case, I had null dereference, and I had an out of bandwidth. Out of bandwidth was the information. And let's see a second vulnerability. It's even simpler. Don't worry, it's going to be very simple. It's not always the management of dynamic memory. Let's have this debug, spot the bug here. And it is a pure FTPD, and now it is the most popular server nowadays. There are vulnerabilities like this one, and that's obvious, and that was a month ago found. Tell me where the vulnerability is. Raise your hand, and we're going to give you a reward. You know about it. Look at this. What's the bug here? Spot the bug. Use the microphone, sir. We cannot hear you. Thank you. We cannot hear the speaker, sorry. So, I'm going to explain it. It's valid what you're saying. You've got the idea. You've got it. You've got it. What we have is a main comparison. We are just getting the length of string 1. And here, really, the sorting fields supposing both strings are equally long. If there is equal length, nothing will happen. If S2 is smaller than S1, we'll have a string comparison function that will have an out-of-band width. And this vulnerability that was reported less than a month ago was there, and it's not complicated. It's very simple. And you can see it, spot the bug. So you've got the reward. You did a great job. Thank you. And it's what I said. It is a read problem that affects, and that's the explanation I've given to you. We've seen real vulnerabilities, real software, but the thing here for all of us is how to find it, because telling what was found is not the main thing, it's how you found it. Response is easy, or fuzzing, it's fuzzing. Fuzzing, it's a bit complicated. It's a big fuzz, but not this. This is what you imagine. Now, it is this sort of intelligent fuzzing, intelligent fuzzing. The idea here is to apply expertise to fuzzing, intelligent fuzzing. and let's see how to find vulnerabilities. And we could have other techniques, but as we have a short time, I'm going to mention intelligent fuzzing here. So the complexity of the problem, and we see here why are we going to use fuzzing in an intelligent mode. Let's have a file, and we would like to fuzz this. Fuzzing will try to swap contents. If there was 1 kilobyte length and each byte might have 256 combinations, we have a problem of 256 by 1024 total combinations, possible combinations. That's a lot, but it is a lot of a big thing. But size is important here. Then here, size is important. Size does matter, yes. You can laugh, but it does matter. First technique of intelligent fuzzing. First of all, it's mutation scheduling. Mutation scheduling, and the fuzzers like AFL or libfuzzer are evolutional type fuzzers. Let's describe the context and talk about the algorithm, the theory that we've used at the university. Fuzzing, the well-known fuzzers are evolutional process, and you have to reiterate things. But how to select candidates might have us conducted to a good port, or we could waste our time without getting any result. So what I'm going to do here is I'm going to compare fuzzing process with a tree, or with the search space when we have a tree. That's a deep pathway. Node 1 will be parental, the initial entry, the image we would have here, and we're mutating this, and we're performing changes, and we're changing levels, and we're going down. We have children here. We have 6 levels, 6 mutations were performed, and those are the possible combinations. Also, we have here the cross approach, the width. We try to have as many combinations as possible prior to going to the next level. And this is what I expressed, or I explained to you, because we have the heuristic algorithm. It is such a big problem that we cannot approach this using brute force. We have to have the heuristic approach to have a shortening space, a shorter space. On the one hand, we have initial inputs on the left-hand side. On top, we have the entry inputs. There are mutations. By defect, those mutations are flip the byte, are concatenating files, or adding words from dictionaries. And with the mutated files, they will execute the swap or mutated files, and we see the coverage of the code. We see the functions it went through. If the new mutated files added new functions, we have new coverage, then it considers this as interesting, and they add it as the queue of future entries. In an iterated mode, we are simulating a circle, and we go back to taking interesting files, mutating them, and cycle after cycle we make it happen. What I'm going to show you is that AFL assigns a bigger effort to those inputs that are located at a deeper location. We see the mutation trees, and by default, we have a higher score when it goes deeper in the search tree. If we have many more mutations, it's more interesting for AFL, and we have top priority then. Nevertheless, there is another approach, which is AFL fast, which is a force method created by Marcel Bern, where we have a different approach. Instead of going deeper and deeply, what we have here is that we go wide. So this is the AFL fast approach. Instead of going deeper and deeper, we take branches that were considered as no interesting, and we make them evolve, same like the other ones. And we have then this path is a cross approach. Instead of going deeper and deeper, we go in this wide approach, the width instead of the depth. Width instead of depth. This is the AFL++. You know AFL, of course, we all know AFL, but AFL++ is not as well known. And the original project is not updated sometimes, and there are people having added things to AFL. So AFL++ is a fork, it's an AFL fork, allowing us a simple option, which is a P option. We choose your schedule you want to have. When I say schedule, I'm mentioning the time elapsed, time we're going to let till we go towards the lower level. So we're going to wait our search, and we're going to have we'll go deeper or we'll go wider accordingly. That's an example of AFL++ with the different schedules. As it is a heuristic approach, we cannot say for sure that one is best. We have here, they're always a part of randomized processes, but it is interesting for you to know. You can imagine a project with a standard AFL schedule. It's not optimal for this, but you might save time and iterations if you decided to choose another schedule. So I'm summarizing the theory. I know it's very, very clumsy, very difficult, very cumbersome, but you launch 4 or 5 schedules during the first hour, you see results obtained, and based on that you select to go deeper or to go wider. And you will see that you get better results in a rapid mode, and that's an advantage for you to consider. As I said, it's a heuristic process where you have the experience of the analyst combined with the computational power. It is like artistic and scientific approaches. It is like this combination. Don't laugh at Danny. I'm going to sip some water. We have here the second half of my presentation, which is not as difficult as this first one. The first part was more difficult. The second one is the structure away. So this is a new term that is fashionable within Fuzzing world. We all know machine learning. We all know cyber resilience or resiliency. We'll have blockchain. We have data mining. We have synergy. But I'm going to give you an example of a paper that was published in Spain recently, The End of Programmers, the Way We Know Them Now. And it's to ascertain and to differentiate things. Look at the technical part, but let's not be sort of confused by terminology. The end of programmers, the way we know them nowadays. And that's something that's here to stay, and that's something we'll get in a short while. And they said things like, we need more programmers, many more programmers, but at the same time, machines will be better than programmers. And the guy said, thanks to artificial intelligence, machine learning, the source code will be written by machines in such a mode that programmers will be needed the way we know them now. And they said websites will be self-designed with big data and automation processes. Fox, said the speaker. So I think this is crazy, absolutely crazy.
But don't acknowledge, don't thank me, thank the author of the publication. So what is fuzzing? This is a little bit of a word. So we are talking about custom mutators, AFL effect, and they do bit flip, meaning turning bits around. They put words in dictionaries, so very simple mutations that are not adapted to our specific program or domain. So with the extractor web fuzzing, we can do mutations programmed by us. So we can use grammar to generate points that are meaningful for our program. So when can we use that? Because we talk about fashion, we talk about words, but it's not easy to put them forcefully everywhere. So when do we use structure-aware fuzzing? It's like machine learning everywhere. Machine learning for breakfast, machine learning for dinner, and then artificial intelligence. So it's not always useful to use mutators, but for some problems, this is advisable. For other problems, this is not advisable. So when is it useful to use personalized web muting? So when we have a simple pipeline architecture, which must not confused with processors infrastructure. So we have a modular system, and the output of one module is the input of another one. So it's a linear thing and ordered. So this is simple, because if the fuzzer is stopped at the first step, let me give you a real example, GCC. If you studied programming, compiler programming knows this very well. The lexic analysis will do away with a lot of iterations without studying grammar or semantics. And why is that? Let me give you another example. JavaScript engine. It is like that because if our entry data are not consistent, you mutate or corrupt the lexical language of our code. This is another example, JavaScript engine, and same thing happens here. If we have a JavaScript engine and we start fuzzing randomly our input, the only thing we'll do is going to break it, and we will not be able to move on to the second phase. When is it useful to use personalized mutations? When we have programs that are not modular, a lot of extern, a lot of variables that are shared throughout the program. So low modularity. Low modularity makes tackling the problem very difficult if we have to separate each module. So this image with the wire is a little bit forced, but I'm sure the technicians in the room will understand this very well. But as the image says, enjoy life. So you can use this when you have complex restrictions. For example, when you want to analyze APIs or real-time protocols, TSP, etc. So if you know web analysis, if you have an API like this one, and if you're not able to complete the first stages of the API lobby, or when critical information is sent for identification, if these critical stages are not followed and we do that randomly, we're going to be stopped and stuck at the first stages, and we will not be able to make the rest of the API run or function. Manually, you know that you have to go through the first step and then the second stage. But you have smart fuzzing with personalized protocols. All the stages can be done automatically, easily. So this is a good example of how structure-aware fuzzing easier. So this was created by Samuel Grass. And it's a very good example how he used personalized mutations to work with Google Chrome. Everything is well detailed. This is a master thesis for his PhD, I believe. So if you're interested in that, you can go through this document and this thesis or dissertation paper, because it's very complete. So personalized mutations is useful, but when personalized mutations are not useful, when we have simple restrictions. For example, we need to use structure-aware fuzzing because we have a checksum, which is a code verifying the integrity of the file. For example, image format with checksums. So in this case, you don't have to use it. You don't have to use mutators. So keep it easy. So get and include the checksum in the code and continue using normal mutations. It is not useful either when we have a modular, well-programmed system. So, for example, VLC player. This is highly modular program. Each thing is completely separated from the rest. On the one hand, we have the MUX, the OGG demux, then the AVI demux, and the MPEG demux. So you take each module, you fuzz it separately, and then put the results together. And then after the second part of the presentation, let's see some demos for you to be really thrilled. So this is a vulnerability, leap XML. So I just wanted to show you this leap XML 294. So as you can see here, what corrupts the software and the library is this little part here with the X25. The rest is it's a standard XML entity. So what if we wanted to find this vulnerability using XML? So what is the most simple approach? Well, AFL plus dictionaries. This is the way to solve this. So what did I do? I took the content of the entity, I separated in little tags, little chunks, and I used my own dictionary plus AFL. So this is the result after 4 hours and 10 minutes. No bugs were found with this dictionary. Why was that? Because mutations are meaningless. So we take all the components of the dictionaries, ordered randomly, and finding the correct order provoking the bug. 4 days, 4 weeks might elapse, or maybe we will never find it. So I created AFL++, which allows you to use personalized mutations. I created a personal mutator, which is very simple, this one. And what I made was giving it a certain logical order to the structure. So a top tab at the beginning with an entity, and having the opening and ending characters well structured. So I don't know if I will be able to show the video clip I wanted to share with you. Probably no audio or anything. Oh yes, everything works well. Okay, I'll try to explain this to you. So I'm going to the AFL parameter. Someone is not using the mic. Yes, it's the same. It is the same. Yeah, good for you. So I set up the project. I established the AFL compiler, and it's up there, as you can see that. We are terribly sorry, but music is at the same time as the speaker, so sorry about that. So you can see the AP, and again, music and the speaker on the same mic are impossible. And then we have to compile. This is the section I want you to see. This is the library we compiled with our custom mutator. So this is the most important part. So I did this with the AFL custom mutator library, and I put the dynamic compiled library. We can put everything. The sky is the limit. So grammar, mutations. You can use databases to analyze code, etc. You can include deep learning or whatever you want because the sky is the limit for this. So we export this, and what we do is to compile custom mutator in a dynamic library, and then we run the fuzzer. So I enabled a SAM as well, because if you will use sanitizer, the possibility of finding the bug is the chances to find the bug are higher. So I launched AFL. Before we had 4 hours. As you can see, we have the custom mutator, and it took only 7 seconds only to find the bug. With a standard AFL before, and the dictionary, the standard dictionary, the bug was not found. I know that you all like the song, says the speaker, but I have to stop it now. Also, you could go beyond. We could go beyond even. So imagine we have an ambitious project. We have hyper hackers. We have a hat. So we are hyper hackers. Imagine we have a more ambitious project and we want to use a standard format. So we have a protocol buffer program from Google, which allows structured information to be simply defined. Here you have an example. It's similar to XML, but simpler. And there is a library called libprotobufmutator that uses this structure, and the program fuzzes it. So you create the file .proto, and you forget about creating your customized buzzer. So you use the XML structure or PMG, and the library mutates the content without corrupting the file, which is the most interesting part for us. Finally, just a warning. Every time you use personalized mutations or custom mutators, when you personalize the fuzzing process, unavoidably you are missing some cases. We go more in depth in our search, but these cases that are rare are missed. If we use a structure in our fuzzing process to get more cases, rare cases that are out of the structure are missed. So whenever we have a simple heuristic process, we need to strike a balance, and we need to be aware of what we do, not use it for the sake of using it. This is the last part of my presentation, and I think we will have time for questions and answers. So, domain-specific feedback. This is probably the most uncommon part of my presentation. So let's overview what is node coverage. This is a normal file, and you can see in different colors the different lines that have been executed in my software. So in green are those executed, in red are not executed for the inputs I put. On the left, the number of times the lines were executed. So this is a summary of the project. For each file, you will have the percentage of codes executed, red or green, depending on the amount of codes executed. So LCOV, GCOV, programmers know this. This is what we call node coverage. Whenever something is executed, is green. If not, is red. libfuzzer and AFL use edge coverage. What is edge coverage? Instead of marking, and this is an example on C, instead of marking each instruction executed, what we have is the leaps we make. Instead of saying, I executed instruction 1 or 2, we said from instruction 2, we move to instruction 4, between 3 and 5, which enables our more combinations, and we can cover more combinations as well. There is a more powerful coverage, which is complete path coverage, meaning all the steps since the software was launched until the end. So this is the entire path. Why did I explain this to you? Because I wanted to show you the ideal scenario at the beginning, or the initial corpus to start your fuzzing process, meaning initially and theoretically, in an ideal scenario, you should have covered all the edges, meaning lib fuzzer, AFL, so you could cover 70 to 80%. You should create manually compiling images, audio, videos, internet. So you have an initial corpus covering the entire code of the program. It's hard to get, but this is the ideal initial, the initial idea, I'm sorry. And the fuzzer should find strange ways for a human to imagine or cover. And at the same time, finding all the possible states, because when the code is covered, however, we should try variables and the possible values for each variable. This is what fuzzer does. But if we want to get efficient fuzzing process, we need to provide it with sufficient input case so that they are completely covered. So this is a bad joke, actually. When the code coverage is not enough, as you know, AFL and deep fuzzer followed coverage, I'm sorry. So if I change 3 letters of the file and I am at the same place, no more coverage has been obtained, so I forget about it. But imagine you have covered 100%. Google Chrome, an ambitious project. Everything is covered. However, bugs showed up that were not found by our fuzzer. So having 100% coverage is not enough. We need to find other metrics to go beyond new memory states and new combinations. This is what Fuzz Factory tries to do, which is a new AFL, quite recent, that provides us with new metrics to feed our fuzzer. So we have covered the entire program, but we are going to find new metrics for interesting cases. And let me show you some of these cases. One metric that would allow us to implement Fuzz Factory is the length of execution paths. For example, we are going to try and make our input to execute as much instructions as possible, as many instructions as possible. The more instructions, the better it is for us to find errors. So the possibilities of finding failures are bigger. And we implement another metric which is very interesting. Beyond the code coverage, reserves of dynamic memory. So the input of our fuzzer will maximize calls to calloc, malloc, etc. Why is that? Because dynamic memory reserves are conflictive. It's easy to find failures when using dynamic memory. So we prioritize inputs that use dynamic memory massively. And the last example is this one. It is common for our software to have macro assets, or the macro assert, I'm sorry. So if the file descriptor of an image is not valid, the image is not processed. So verification closed and shut the program. So we are not using fuzzing efforts. We are not moving forward in the fuzzing process. So we are interested in having inputs that do not activate these asserts, because if error happens, errors are or must be due to bugs instead of due to asserts. So we need to reduce the possibilities of having high numbers of asserts. I think you endured the presentation. I think the Camela song was good for you to be holding on to the end. I didn't hear people snoring or anything, but let's go to the conclusion. 3 points. When you work with the heuristics with heuristic algorithms, not only those applied to fuzzing, there's always a randomness factor. So results will never be the same between the different executions. There's always something due to random chance, and then something due to the execution of some person. Then the search space is huge. Not all the possibilities could be found. It's not the entire universe, just a little part of the universe. So when we use personalized mutations or any other technique allowing us to go further, we are cutting things down, magics that does not exist. If we use 100 iterations deeply, we miss something widely. And then the human factor, which is sometimes forgotten and is the key. Even simple fuzzers as AFL, this is the key. This is going to be good to find bugs and failures in Google Chrome, for example. So these use simple buzzers. The difference is who uses them. So conclusion, that was boring. We are at the end. Before concluding, I'm going to publish on my Twitter account a little challenge. Some of you have won the prize already here. And for the rest, 15 codes to use in the gift hub store with the merchandising and T-shirts. And the first people to answer correctly to the challenge I'm going to launch, a code will be given to the 15 first people with the code that will be used to exchange for a T-shirt at the store. Thank you very much. That was a pleasure for me to be here. So many questions. I see a lot of questions in the audience. So there are two questions over there. I got a Twitter messages saying, oh, yes, please ask him some this or that. Where is Antonio? Antonio was sending me questions on Twitter. Good morning, Antonio. Congratulations for your presentation. You didn't mention press banking, but that was good anyway. Okay, I just wanted to ask you your opinion about symbolic execution. Is this good or not? No, this is not like smoke that disappears and vanishes, but the technique is in the early stages, and my opinion is that concordant execution, symbolic execution is even at an earlier stage. So when we talk about real software, about complex software, but the possibilities are lower than using AFL, because AFL, for simple things, the results are better. It's better than symbolic execution, which is good for little things, but for what? For checksums? When I solve the problem with checksums, that's the end of symbolic execution. So AFL, simple AFL is better. So more questions? Oh, no more questions? Okay, thank you. Antonio, it seems there's no more questions. Thank you very much for your presentation and for showing and sharing your job with us.